Hi, I'm Xenowave and welcome to my Beginner to Advanced Sound Design series. In this video, I'm going to talk about the properties of sound and how you can analyze or measure those properties. In this series, I will try to explain everything as though you are brand new and know nothing, so we can all be on equal footing as we progress towards more advanced concepts and ideas in sound design. So let's begin with what sound is. Sound is a vibration. In order for sound to travel, it needs something called a medium to travel or vibrate through. Mediums can be a liquid, solid, or gas, but in this context, I'll only be using air as a medium. So when sound travels through air, it is vibrating the air pressure. The vibrating air pressure then travels as waves and hits our ears, which our brains interpret as sound. The first property I'll go over is amplitude. Amplitude, also known as volume, is how intensely the air pressure changes, which our brains perceive as how loud a sound is. A louder sound covers more distance and a quieter sound covers less distance. This is a decibel meter, a tool that's used to measure the amplitude of sound in a unit called decibels. It's scaled logarithmically, which basically means we can measure a wide range of numbers in a more compact form. Logarithmic scales are pretty common in the world of sound. Alright, so let's see it in action. I'm going to play a sound and we're going to see how many decibels it is. So it looks like it peaks at around negative 8 decibels. So if I bring my sound down to silence, it will hit negative infinity decibels. So let's look at this. Just like that. When a sound goes over 0 decibels, we get a type of distortion called clipping. So let's see what that sounds like. So I'm right here. Watch what happens when I push it even a little bit past 0. We can hear that the sound is distorted a little bit. And if I push it further, here's what we get. Keep in mind that the information on clipping really applies to digital audio, not really acoustic audio. But I'll go deeper on digital audio in a little bit. The next property of sound is the waveform of sound. The waveform is the shape in which the air pressure vibrates. Speaking of waveforms, there are 4 basic waveforms that are important to know: the sine wave, the triangle wave, the square wave, and the saw wave. So this is a sine wave. The sine wave is a singular pure tone and is the building block of all sound. Here's what it sounds like. This is a triangle wave. It sounds similar to a sine wave but has a bit of a richer sound to it. Here's what it sounds like. This is a square wave. I've also seen it referred to as a pulse wave, and it sounds much richer than a sine wave or a triangle wave. Here's what it sounds like. And this is a saw wave, which sounds the fullest out of the 4 basic shapes. Here's what it sounds like. They're all important in their own ways, and we'll explore that as we go along. In this video, though, I will mostly be using a sine wave for most of my examples. This is an oscilloscope, a tool that lets us analyze waveforms. I'm going to put the master volume down so I don't have to talk over the sound as I'm playing it. So on the x-axis we have time, and the y-axis is amplitude. So if I adjust how loud it is again, and I bring it to, let's clip it actually, yeah. So as you can see, if we clip it, we can see that this is just kind of, well, clipped off. It gets cut off once it hits past 0. And if we hit silence, just a flat line. This horizontal line in the middle here is called zero crossing, and is basically a point of rest where there's no change in air pressure. A waveform is in the positive when it is above zero crossing, and it's in the negative when it's below zero crossing. The state of being positive or negative is called the waveform's polarity. If a waveform has positive and negative polarity, like the sine wave over here, it's called bipolar. If a waveform only has positive polarity or only negative polarity, then it is unipolar, like this. DC offset is how far the waveform is from the zero crossing line. So for example, for this waveform, you could say it has a positive DC offset value because it's above the zero crossing rather than below it. So that's DC offset in a nutshell. The next property I'm going to go over is oscillation. Oscillation is just when something moves back and forth repeatedly. In the context of sound, whatever thing is oscillating is moving the air pressure back and forth. This is how sound is generated. If I wasn't clear enough, the line that draws the waveform in the oscilloscope just represents the oscillation between high and low air pressure when a sound is being generated. In order to have oscillation, we need something that oscillates, which is called an oscillator, which is the thing that moves the air around fast enough to generate sound. For example, speaker cones are oscillators. When speaker cones move back and forth at some audible rate, it will generate sound because of how the speaker cone oscillates the air in the speaker. By the way, please bear with me if I sound redundant. I just want to be thorough in laying out a strong foundation for understanding sound design. The next property of sound I'm going over is frequency. Frequency is the speed at which the sound oscillates, and it is measured in cycles per second, also known as hertz. This is the spectrum analyzer, a tool that lets us analyze frequencies on a frequency spectrum. So the x-axis is frequency, and the y-axis is the amplitude of said frequency. Like amplitude, frequency is measured on a logarithmic scale. There are way more high frequencies than there are low frequencies. So if we look at 10,000 hertz to 20,000 hertz, it's this tiny space over here, right? But if we go from 20 hertz to 1,000 hertz, it's way bigger than just this 10,000 over here versus this 1,000. For more clarity, I'm going to play a sine wave at 3 different frequencies from lowest to highest so you can have a better look at what's going on. So I'm going to bring the volume back down. In the example, if you look at the oscilloscope, the lowest frequency had the least amount of cycles. And then as I increased it, you can see the cycles grow more and more. And this is what we mean by cycles per second. The more cycles there are in a waveform, the higher the frequency. And in the frequency spectrum, we just see it move from left to right, like this. The human ear has an average hearing range of about 20 Hz to 20,000 Hz, and as we age, we start to lose some hearing. So the average adult can hear up to 16 to 18,000 Hz, and as you get even older, that number starts to decrease. To defend against hearing loss, I suggest investing in a good pair of earplugs and just wear them whenever you enter a loud area. The next property I'm going to go over is pitch. Pitch is how high or low a sound is. A sound can be made up of multiple frequencies. The lowest frequency in a sound is called the fundamental frequency. Pitch is whatever hertz value the fundamental frequency is. Pitch is more commonly represented using the musical alphabet notes like F sharp, for example. So if I play a square wave, for example, I see all those frequencies up there, but to find the pitch of the square wave, all I need to do is look at the lowest frequency. So that's around 262 Hz, which is middle C. Quick side note, if you don't know the musical alphabet and you want to learn it, watch the first video of my Beginner to Advanced Music Theory series. The link to the playlist is in the description. The next property of sound is phase. Phase is just the position of a waveform. It's usually measured in degrees. Here's what happens when I change the phase of this sine wave over here. It just moves along the cycle just like that. I don't think I've said it before, but the amount of time it takes for a waveform to complete a full cycle is called the waveform's period. Since frequency is defined as how many cycles happen per second, the faster the period, the higher the frequency, and the slower the period, the lower the frequency. With all that being said, I'd like to point out a very important relationship between phase and frequency. By the way, this tool I'm using over here is called an audio editor. So I have a single cycle sine wave over here. If I play it, you hear it click, but if I loop it, you hear it cycling at some frequency. With this button right here, I can control the phase of my waveform in real time and how fast that phase changes. So let's see what happens when I do it slow. We get a low frequency waveform. So if I speed it up, I increase the frequency or period of my single cycle waveform. So what does this all mean? This basically means that frequency can be defined as the phase's rate of change. In short, if you change a waveform's phase, you can influence its frequency. That's important to remember for later in the series. The next property I'm going to go over is called interference. Interference happens when multiple waveforms are playing at the same time. When two waveforms are being played together and the result signal is louder, it's called constructive interference. Here's an example. So we know that the sine wave from before peaks at around -8 decibels, right? Watch what happens to our amplitude when we add in a copy of that sine wave. So now it peaks at around -2 decibels. That's constructive interference. When two waveforms are being played together and the result signal is quieter, it's called destructive interference. So I'm going to raise the volume of this copy, and I'm going to reverse the polarity, which just means that the positives are now negative and the negatives are now positive. Watch. So now it's peaking at around -15 decibels. Phase cancellation is another name for destructive interference. Phase cancellation happens because the positive part of a waveform is being played at the same time as the negative part of another identical or similar enough waveform. So watch what happens when you play two identical waveforms together at the same amplitude, but only one has reverse polarity. We get total silence just like that. So that's an example of a perfect phase cancellation. Most of what I've explained so far pertains to both acoustic sound and digital sound. What I'm going to explain next is specifically how digital sound works, since that's what we'll be dealing with for the most part in this series. So how does digital audio work? In the digital waveform, there are these tiny bits of data called samples, and they're basically numbers that represent the change in air pressure over time, also known as the waveform. When the waveform is completely formed, the computer sends that set of data to the speakers, and the speaker cones will oscillate in the shape of the waveform that was created by the samples at whatever frequency and phase the computer tells it to. The amount of samples per second used to form a digital waveform is called the sample rate. I like to think of samples as the sound equivalent of pixels. Generally speaking, the more pixels there are in a picture, the higher quality the picture will be. The more samples there are in a sound, the higher quality the sound will be. Of course, there are exceptions in special cases, but that's the gist of it. To complete the analogy, samples will be the pixels of an image, and sample rate will be the resolution of said image. Just to be clear, sample rate is measured in hertz because it's however many samples are used per second. 44.1 kilohertz is a common sample rate in a lot of media and programs, but some programs allow you to change it. In the world of digital audio, we have something called the Nyquist frequency. The Nyquist frequency is half the sample rate, and whatever frequency information goes past the Nyquist frequency will fold backwards. So let's investigate what I mean when I say the frequencies fold backwards after going past Nyquist. So we know that this project has a sample rate of 44.1 kilohertz. If we divide that by 2, we get 22.05 kilohertz, which is our Nyquist frequency. So let's see what happens when we generate frequencies past Nyquist. I suggest you turn your volume down because we'll be dealing with some high frequencies. So first I'm going to make this sine wave really high. And then I'm going to modulate this sine wave's frequency by another sine wave. Don't worry about the technicalities of what I'm doing. I'll explain that in the cross modulation video. Alright, so now I'm going to raise the pitch of this other sine wave. So if you looked at the frequency spectrum as I was changing the frequency of the second sine wave, you would notice the frequency is sweeping up and down in a seemingly random fashion. This is the result of the frequencies hitting Nyquist and bouncing back. Another important thing to note is the further a frequency goes past Nyquist, the further it will bounce off of Nyquist. So for example, if I have 6000 Hz past Nyquist frequency, the resulting frequency is going to be Nyquist minus 6000 Hz, or in this case, 22.05 kilohertz minus 6000 Hz, which is 16.05 kilohertz. For more clarity, I'm going to push frequencies past Nyquist again, slowly. So we see some frequencies coming down, and as we get higher and higher, the frequencies that were previously around 20K are probably around, let's say, 25K, but as I push it further, we're going to start seeing some low frequencies because we're going to start hitting frequencies that are around like 40K, and it's going to wrap around real hard. Like this guy right here. And so on. This behavior of frequencies going to Nyquist and wrapping around it is called aliasing, and it's something to be aware of when doing sound design with higher frequencies. Alright, so now let's get into extremely important concepts that serve as the basis for everything we do in sound design, which is basically the ideas behind Fourier's Theorem and the Harmonic Series. So first, Fourier's theorem states that every sound can be represented as some combination of sine waves at a certain phase, amplitude, and frequency. Next, we have Fourier analysis. Fourier analysis is when you take a sound and analyze the composition of that sound by looking at the amplitudes, frequencies, and phases of the sine waves that make up that sound. And we have the Fourier series. The Fourier series is the actual combination of sine waves at certain phases, amplitudes, and frequencies that make up any given sound. To support these ideas, let's go inspect some sounds. So I have a random vocal sound that I picked. Here's what it sounds like. And when we zoom into the sound, or any sound, we're going to see a bunch of squiggles. And these squiggles are the result of summing together sine waves at various phases, frequencies, and amplitudes. Just like that. This sound here is a piano passage I've taken out of context. Here's what it sounds like. And if we zoom in, it's the same old story as before. More squiggles. Also, don't mind the two lines. This is the stereo audio, which I'll explain in the next section. For this sound, it's just a heavily processed bass taken out of context. Here's what it sounds like. And same old story. Zoom in, we get all these squiggles. The sine waves that make up sound are called partials or overtones. You can use those two words interchangeably. A partial is a singular sine wave at a certain phase, amplitude, and frequency. As stated before, the lowest partial of any sound is called the fundamental frequency. If the frequency of a partial is a multiple of the fundamental, then it is called a harmonic partial. This is common in instruments and tonal sounds, and even your own voice. So a quick example of harmonic partials would just be adding in these sine waves. So let's just listen to this. And those are harmonics. If the frequency of a partial is not a multiple of the fundamental, then it is called an inharmonic partial. This is more common in metallic sounds and quote-unquote unnatural sounding sounds. Since this program only lets me put in harmonic partials, I'm going to make a copy of these harmonics and output them. And then I'm going to shift the tuning a bit, and this is what it sounds like. So that's an example of an inharmonic sound. Not the best example, but like I said, unnatural. And then I could try randomizing this or something. And that's what that sounds like. So all this talk about harmonics and partials brings us to the harmonic series. The harmonic series is a naturally occurring pattern where every partial in that set of frequencies is a multiple of the fundamental frequency. So now let's go through the first 7 harmonics of A4, which is 220 Hz. There's our first harmonic. There's our second harmonic, which is just an octave. There's our third harmonic, which is a fifth past our octave. There's our fourth harmonic, which is just a perfect fourth above our previous harmonic. There's our fifth harmonic, which is a major third above our previous harmonic. There's our sixth harmonic, which is a minor third above our previous harmonic. And there's our seventh harmonic, which is approximately a major second above our previous harmonic. And now we have a sound we can play with. And with these 7 harmonics, I can change the amplitude of these sine waves to get different sounds. If we look at our frequency information in the spectrum and compare it with our notes over here, we'll see that everything matches up. So first harmonic is 220, second one's 440, third one's 660, and so on. I'm looking at this little section over here, by the way. Yep, 880 and so on. Also, if you don't know what I meant when I was talking about octaves, fifths, fourths, major third, minor third, and so on, those are called musical intervals. And if you want to learn about those, just watch the second video in my music theory series. Let's look at the harmonic distribution of the 4 basic waveforms now. Starting off, we already know that the sine wave is just a singular partial, nothing else to it. So here's what the triangle wave looks like. We have odd harmonics coming down in volume, and some of the harmonics have their phases rotated. If you take away the phases, actually, it stops being a triangle. So it's pretty interesting. If we look at a square wave, we'll see that it's just odd harmonics slowly going down like that. And if we look at a saw wave, we'll see that it's all the harmonics going down in volume, like that. To be very clear, not every sound can be broken down into the harmonic series, because there can be a mix between harmonics and inharmonics in a sound. However, every sound can be broken down into its Fourier series, which includes both harmonics and inharmonic partials. I just wanted to point that out. Now that we know about the Fourier series, harmonic series, and so on, let's get into timbre. The timbre of a sound is how the partials of that sound are distributed. You can think of timbre as the identity of a sound. This distribution of partials defines this saw wave. So if I mess with this distribution, I'm messing with the timbre of the saw wave itself. So if I do that, I kind of ruin the sound a bit. Versus just the original. I can do all sorts of things to it. And there's my new saw wave timbre. Or it's not even a saw wave anymore, really. It's just whatever this is. And that's really all timbre is. If the speakers you're currently using are mono, you won't be able to fully hear or perceive the stereo field, so I suggest you watch this part with headphones or stereo speakers so that things can make a bit more sense. Okay, the next property is stereo, so let's go over the basics of stereo sound. The first thing we have is the stereo field. The stereo field is what gives sound its placement in digital audio. This tool right here is called a vectorscope. It visualizes the stereo field so that we can analyze the stereo information of sound. In the vectorscope, the y-axis is amplitude, and theta is the direction the sound is coming from, measured in degrees. A speaker channel is just a speaker that's used to give a sense of direction. For example, in a common sound system like headphones or common stereo speakers, there is usually a left and right speaker in which sound comes out of. If you have one speaker, then it only has one channel, and that means there won't be a sense of depth, width, or space, however you want to say it. Monosignal just means one signal. It only needs one speaker to be perceived and gives no sense of direction. For example, this saw wave signal is mono. That's what it looks like in the vectorscope, just a straight line in the center. Stereo signal just means multiple signals. These signals can be used to give a sense of width and direction. Before I go over an example of stereo, we need to go over panning first. So, the panning of a sound controls which speaker channel the sound comes from. Again, if you don't have headphones or stereo speakers on you right now, you won't be able to perceive what's about to happen in this next example. Alright, so let's pan this saw wave all the way to the left first and see what that sounds like. Only our left channel is playing. And if we do all the way to the right, only our right channel plays. And everything in between, that's what that feels like. In order to make this a stereo signal, we need two signals. So if I add in a second saw wave, we'll get this. This is technically stereo, but there's no stereo width, which is how wide a sound is. In order to widen these sounds, the first thing I'm going to do is pan them in opposite directions to some degree. And then for one of the saw waves, I'm just going to change one thing, like the phase, for example. And here's what we get. If you're listening on stereo speakers, you should be able to hear the difference between this stereo signal and this mono signal right here. So to sum it all up, in order to have a wide stereo signal, we need to have two different signals panned opposite of each other and have one of them be slightly different from the other signal. So in this case, I did phase, but we can also do frequency or pitch. And that's what we get. The next thing to go over is the Haas Effect. The Haas Effect is an effect that occurs when two sounds are played within a short amount of time from each other, approximately 40 milliseconds, and the sounds are panned opposite of each other by some amount. This tricks our mind into thinking that a sound is stereo because the Haas effect causes phase differences between the left and right speaker, which causes us to perceive stereo width. I have two clap samples here. One is panned all the way to the left, and the other is panned all the way to the right. But if I play them while they're lined up like this, we only get a mono signal. But if I shift one of them like that, we get a stereo signal. Huge difference. And of course, it doesn't have to be all the way left or right. We still get the effect when it's like that. Just keep in mind that the sounds need to be played almost at the same exact time. Otherwise, we'll perceive them as two different sounds, like this, for example, versus this, or this. One downside to using the Haas effect, however, is that you can sacrifice the integrity of your sound. So if I have these lined up, it sounds nice and strong. But if I use the Haas effect, it'll sound a little weaker. And this is the result of phasing. But if we go back and make the panning of these sounds 100% left and right again, we won't hear the phasing as much. We're going to have some of our power back, like that. So just keep in mind how you set up the Haas effect when you use it in your own sounds. So now let's get into mid-side signal processing. This is a different approach to mono and stereo signals, which allows us to process the mono and stereo parts of a sound separately. So the mid signal is just the sum of the left and right speaker channels, which results in a mono-only signal. And the side signal is just the difference between the left and right speaker channels, which results in a stereo-only signal. So I have a song here and a tool called the mid-side EQ that allows me to isolate the mid and side signals. Here's what the mid signal sounds like in this song. So I'm going to turn off the mid signal and turn on only the side signal, and here's what that sounds like. If you didn't hear anything when I played the side signal only, then you're probably listening on a mono sound system. Here's what it sounds like when both the mid and side signals are playing. One important thing about stereo audio in general is that you can't really have a strong sense of stereo width without a strong mono signal to contrast it with. So make sure your mono signal is nice and full, and you should have an easier time establishing a wide stereo signal. So that's pretty much all I wanted to talk about in this video. In the next video, we'll go over synthesis fundamentals. If you have any questions, please let me know, and have an awesome day.